Hello and welcome to Liberty Science Center. We are now going to start our presentation on how to dig up a giant dinosaur.
Hello, everybody. Thank you guys so much for joining me. My name is Jason Schein. I'm a paleontologist at the New Jersey State Museum. And I know we have some old friends joining us right now, some new folks, some colleagues. So again, thank you everybody for joining us. As I said, I'm a paleontologist at the New Jersey State Museum. But today I'm joining you guys from Jersey City, New Jersey at the Liberty Science Center. And we're here to talk about fossils. Today is, after all, National Fossil Day, if you didn't realize that. And it's a really good opportunity to talk to people about science. We've just gotten done talking to a whole bunch of school kids about science and paleontology. And specifically, I wanted to talk about an amazing opportunity I had several years ago to be part of the team that discovered a brand new dinosaur that was just announced a couple weeks ago and is one of the largest animals ever known to walk the face of the earth. So this was an amazing opportunity for me. And so there are lots of different types of dinosaurs. If you know anything about dinosaurs, you know that there are several different major groups. The type we're talking about today are the sauropods, or the long-necked, long-tailed dinosaurs. I always tell kids that my favorite dinosaur book as a kid was Danny and the Dinosaur, and I know that's a classic. So if you remember that book, that's the type of dinosaur we're talking about today. So any great adventure, part of that adventure is actually getting to your destination. And getting to southern Patagonia, where our expedition took place, is definitely quite an adventure. We fly overnight to Buenos Aires, about 6,000 miles away from Philly. We have to spend the night, and then the next morning we get on another plane and head down even farther south to El Calafate, a tiny little semi-resort town in southern Patagonia. And I often tell people that Patagonia is this very vast and largely uninhabited region of southern South America that crosses into Chile and Argentina. And it's a beautiful area. It's pretty arid. It's vast, largely uninhabited. And just getting down here, it takes quite a lot of work. Calafate is actually a little closer to Antarctica than it is to Buenos Aires. And this is roughly our field area. El Calafate is right there on the southern shore of Lago Argentina, south of Lago Viedma, and just east of the Andes, the Chilean Andes, and all those gorgeous mountains and glaciers. And as I mentioned a couple times, this is a very uninhabited area. Our field area is roughly the size of Connecticut, and in that entire area, there are 3 inhabited dwellings. So it actually reminds me a lot of how Montana must have looked like about 100, 150 years ago. So to get to our field site, we spend a few days in Calafate getting our supplies, and then we drive up a couple hours up this dirt road to the only bridge that crosses the river that connects those 2 lakes. We cross that bridge and quickly get completely off the road and just drive for about an hour, completely off-road and really on just a dirt path to get to our campsite and our field site. Excuse me, this is our field group from 2006. And I show you this mainly to show you just how much work was done by so few people. One of those guys near the middle, Eric, he was only visiting us for about a week or two. So the vast majority of the work, which I'm going to do my best to explain to you, was done by just 7 or 8 of us for 2 months at a time, 2 years in a row. Now, one of the most common questions I get as a paleontologist is, how do we know where to dig? How do we know where to get the dinosaurs? And when I talk to people, I realize what they mean by that is actually 2 different things. The first is, how do we know where on Earth's surface to go to find the dinosaurs? And I always tell them that that's actually a process that's been made fairly easy for us. Over the last century or 2, geologists all over the planet have mapped almost the entire surface of the planet for what types of rocks are found where and their age. So you have to know how old the animals are and their fossils to know where to look. We know that dinosaurs lived during the Mesozoic era between about 250 and 65 million years ago. So there's a great geologic map of New Jersey. All we have to do is consult our maps, do a little bit of research, and we know that all those rocks near the middle, those are the only ones that are about the right age. So we can get rid of all the others. We also know that fossils are only preserved in sedimentary rocks. Igneous rocks are nothing more than just cooled off lava or magma. Fossils don't, and things don't live in that, so they're not going to be there. Metamorphic rocks are just what happens when you take really old rock, bury it deep within the earth, and put a lot of heat and pressure on it. So there's no fossils in there. So fossils are only going to be found in sedimentary rocks. So if we're looking for dinosaurs, we have to find sedimentary rocks that were laid down during the Mesozoic era. And it's as simple as that. Now, when people ask me, the other thing that they mean when they ask me, how do you know where to find the dinosaurs, is something like this. They see this enormous mountain, it's all arid, and they wouldn't even know where to begin. And they mean literally, how do you know where, if I were out there, how would I know where to go? A lot of people think it is some kind of crazy, mysterious process that only paleontologists know and understand. A lot of other people actually think that we just go out there and start digging holes in the ground until we run into a bone. And that's not how we do it at all. If that's the method we relied on, we would never find anything. What we actually do is a job called prospecting. And in New Jersey, prospecting looks something like this. You walk around in a muddy, open pit mine, or you go in a creek up to your knees, and you throw some rocks and gravel from the bottom of the stream into the sieve box. It's just a box with some screen mesh on the bottom. You shake it around in the water. Hopefully what's left are some fossils. And this works fine, perfectly fine for New Jersey and in a lot of places in eastern United States. But most major fossil hunting today looks more like this. You go to very arid and rugged lands where there just aren't many plants and there certainly isn't a lot of water. And I'm putting this circle on there to show you just how big this mountain is. Inside that circle, there are several people, there are trucks, and a lot of our equipment. And our quarry, this is our quarry. Our quarry was pretty big in paleontology terms, but it is tiny compared to the side of this mountain. So how do we find this particular spot? Well, it's just through a process called prospecting. And prospecting is literally nothing more than walking around with your head down and your eyes looking at the ground. You're just walking very, very slowly, and you're looking for anything that stands out that looks like it may look like it's out of place. You're looking for something that may be a different color, a different texture, an unusual shape. And in certain places, like here in Argentina and places where we go in Montana and Wyoming, you find bones all over the place. You literally can't step in some places without stepping on bones. The first thing you want to do when you find a bone is not run up to it and go crazy and jump up and down and yell and get all excited, because there may be a whole pile of bones all around you and you wouldn't know it until you were standing in the middle of it. So when you spot a bone, you just want to look at it, make sure you're not standing in that pile of bones, and once you've established that you're okay, you're not breaking anything, then you can go and pick it up. And then what you want to do is start looking uphill, because that bone probably did not originate from where you just picked it up. It probably originated from a layer of bone farther up the hill, and weathering and erosion caused that bone to break and roll downhill. So what you want to do is pick up the bone, look uphill, and if you're lucky, you'll keep finding pieces farther and farther up the hill. And if you are lucky and you find that trail of bone, like a trail of breadcrumbs, they might get bigger and they might get it to be better and better shape, meaning they've been weathered less. In this case, we've been just that lucky. We have found bones exactly where they're weathering out of the ground, so we know this site has a lot of good potential to start working as a quarry. So our next job is to start carefully and slowly brushing away the loose dirt to see if there are more bones there. In this case, we've established that there are more bones, which is a really good sign, and we also want to establish that these bones are still in good shape. Sometimes you find bone that's still buried, but it may be weathered too much. It may be completely infiltrated by the roots of plants and literally just eaten up by those plants and destroyed. And at that point, we would just move on. It wouldn't be worth collecting that. But in this case, we have our bone layer. Excuse me. We have a lot of bones that is in good shape. So now we know we can start our quarry. And these are just some tools that we use in paleontology. And you can see there that there is nothing crazy and unusual. One of the great things about paleontology is that we use a lot of very, very simple tools, and because of that, fieldwork in paleontology has not changed really in 100 and 150 years since it got started. Tools like this. This is a great trenching shovel. It's small enough that it can be carried all day long if you need to, still useful to dig holes, to scrape dirt off the side of a hill, just about anything you need it to. The other most useful tool that we have is what we call a marsh pick. It's basically like a mini version of a mattox or a pickaxe. And again, it's not great if you're going to be in one spot all day breaking rock, but it's perfect if you're going to be walking around prospecting. It's small enough to be carried around all day. It can still do the job of breaking rock, moving rock, all that kind of stuff. We also use a geology hammer a lot. It's got a nice blunt end, very, very hard for breaking rock, and a nice pointed end for splitting rocks open and digging holes and things like that. And we use a lot of other very simple tools, just regular old paint brushes. And one of the tools we use the most is just a little bottle of regular old glue for putting the bones back together. So as you can see, it's pretty simple stuff. There's nothing exotic that we use, and this is one of the great things about paleontology. Since we use such simple tools, and since they're so cheap, we can do a lot of work for a relatively small amount of money. For $25,000, sent a team of 8 of us down to Argentina for 2 months to live and to do this expedition. And nowadays, in a modern biology lab, they could blow through $25,000 in a week, no problem. So this is one of the things that we love about paleontology and field paleontology. All right, back to the quarry. So now we have our fossils, we have our bone layer, so we need to start quarrying and removing that overburden, or the rock that's on top of the fossil layer. And to do that means a lot of picking, a lot of breaking rock. And in this case, in Argentina, this rock was as hard as concrete, and there was a lot of rock to move on that steep hillside. So it literally took us weeks and weeks of breaking the rock by hand, and then once it's broken, it has to be moved. We have to get it out of the quarry. So that adds to the time. These guys shoveling the rock out, taking out wheelbarrows and buckets. We spend literally at least half of our time, maybe 75% of our time, just getting rid of all that overburden so we can get to the fossils. So the process looks something like this. We're getting rid of all that rock on top of the bones, not so we can take the bone out yet, but just so we can expose the bones and so we can see where all they are and how far back into the hill they go. So this slide shows or demonstrates a nice little principle or a problem that we have. It's a good problem to have. We've removed a lot of that overburden. We see that there are a lot more fossils and bones, so we have more of the skeleton, which is great, but we see that the bones are still going back into the hill. So every time this happens, we have to carefully and gently cover those bones back up with a little bit of loose dirt, and then start blasting away at that hillside again. In this case, we've removed a lot more of the rock. We found more bones, but we have reason to believe that we have found the last of the bones. So we're a little bit relieved. A lot of the hardest work is done. But you can see there how quickly the amount of material that we have to move adds up quickly. And again, that rock is incredibly hard. So every time we have to start working on that overburden again, it's more picking, it's more shoveling, and hopefully you can start to see why this is such a time-consuming and physically demanding process. So the point of all this is to start out with a quarry that looks roughly like this. This is like the first day of our quarry. We've got one bone exposed right there. It's in really good shape, so we're going to start working back into the hill. And after 4 months of work, this is what that same quarry looked like. That white line is there to try to show you roughly how high the ground surface was when we started digging. And you can see there that is tens of tons of solid rock that we removed, almost all completely by hand. It's an incredibly demanding process. And this outline of this bone is to show you where that bone was that I highlighted on the last slide. That's a lot of work by just a few people. When you're doing this, though, you don't do everything with those big tools, the mattox and the shovel. The closer you get to the fossil layer, the more careful you have to be, so the smaller the tools that you use. So that's when we use the geology hammer that I showed you that Sarah and these guys are using. And then when you get even closer, you use smaller tools, which we'll get to in a second. But a lot of people often ask me, what happens if you break a bone? Well, obviously that's not a good thing. We try not to break bones, but it's completely inevitable. If you're in a quarry and you have all these bones and they're laying all over each other like Lincoln logs, you never know exactly where the next bone is going to be. There were lots of times where I would put a shovel down into the ground thinking it was a perfectly safe place to do it, and I would blast right through a bone. And again, that's never good, but it's not the worst thing in the world either, and that's why we bring people like this. This is my friend Jason Poole. who goes down a lot of expeditions with me, but he was there in Argentina. And one of the many things he's really good at is putting fossils back together. He's a paleontologist at the Academy of Natural Sciences, where he specializes just in that, putting skeletons back together. And he always says that it's all right if you break a bone, that's why you make glue. So we do use a lot of glue out there. Now, we're back to the quarry. We're really close to the fossils now. We've gotten to the point where we're so close we have to put down the hammers and we have to start using the really small tools. And by small tools, I mean these, like I have here. A lot of times, this is actually my favorite tool. This is an awl, just AWL. It's basically a glorified ice pick or a screwdriver with a pointy end. And these are really great because obviously you can carry it all day long. You can use it to break rocks open or pry rocks open. You can tap on things. If sometimes a fossil will make a different color than the surrounding, a different sound than the surrounding rock, and you can tell just by tapping on it. And when we get really, really close to the fossil layer, we'll even use dental tools, exactly the same kinds of tools that dentists use on your teeth. In fact, when they're just starting to get dull enough so that the dentists don't want them anymore, that's when we like them the best. So a lot of people say, well, now that you're done breaking all that rock, swinging those picks, most of the physical work is done, right? It's a lot easier after that. Well, it's not actually true at all. We've removed a lot of rock, but we don't want to remove more rock than we absolutely have to. So that often means leaving really narrow trenches to work in, to squat in, lay down in. And at this point, you're removing a lot of very hard rock off of small parts of bones. And that can take weeks when you're working with things like dental picks and screwdrivers. So for weeks on end, we might be laying in really uncomfortable positions like this, busting our knuckles as things slide and move, making our backs and shoulders sore, even muscles that you don't even know you have. This can be just as physically demanding as the other stuff, even though it looks like we're just lounging around. We also learned a really important lesson when we were out there. We would often uncover a really perfectly pristine bone like Chris is doing there on the left, in the left picture. He's got a nice rib that we just exposed. They're perfect, they're complete, no cracks, nothing. And then the next morning we get up, get back into the quarry, and the same bone is completely riddled with cracks, broken into hundreds of pieces. And we realize that, these bones have been under sometimes thousands of feet of rock for millions and millions of years. They've never experienced fluctuations in temperature or humidity, sunlight, nothing like that. So as soon as we expose them, they're getting all those variations, and of course they're going to expand and break up and crack. So that was a costly lesson that we learned, but it's very simple to prevent after that. As soon as we would uncover bone, we would just cover it back with glue, and that seemed to work pretty well. A lot of people ask too, or they're very interested in how we lived out there, because as I mentioned, we were at least 3 hours from town, and it wasn't an easy 3-hour drive on the turnpike. It was 3 hours of hard off-road driving. So what we would do is we would go into town, rest for 2 or 3 days, collect all the supplies that we needed, and then come back out and camp until as long as our supplies lasted, which was usually 12 to 14 days. And in between, it was just camping. We had a very nice flat spot alongside this beautiful river about a quarter of a mile down the hill from our quarry site. And we didn't have very much free time at all outside of the quarry, but when we did, we would decorate our homes like anybody would with some nice Wanako skulls and hip bones. Sometimes there was time to go fishing, but it wasn't just for fun. We would eat the fish. We had enough food, but we could always have used more. So we would do anything we could to supplement this. We would go collect berries. We would eat the fish. We would cook over an open fire beside the river. We would sit there and hang out at night, as long as we could anyway, until we were just too exhausted. Perhaps the most painful thing we did during the entire expedition was bathe and wash our clothes in this river. It was a beautiful river, but if you remember from the pictures I showed a little while ago of these lakes right beside those mountains, all of this water was a glacier not 24 hours ago. So this water is absolutely frigid and painful to force yourself into. But when you're working that hard and that long and under those conditions, you absolutely had to take baths and wash your clothes. There was no way around that. All right, one of the most important things we do as a scientist, and this is true of any scientist, not just paleontologists, is that we are constantly observing things. And in science, observing things just means taking notes. So this is my field book from this past summer in Montana and Wyoming. And every good scientist is constantly taking notes in their field books. And we write down everything you can possibly imagine. What time we got up for the morning, what we had for breakfast, what the weather was like, if the weather changed, what time and when. Obviously, what bones we're working on, where we are when we're working. Just everything you can possibly imagine that will help you 2, 3, 10 years down the line recreate the day are things you want to put in here. But it's not just for us. Before we go out on an expedition, one of the first things we do is not only consult geologic maps, but we will also consult old notes. And many times we have looked at notes from expeditions that happened 100 years ago to help us learn things and prepare for the field. So I'm writing these notes not just for me, but for other paleontologists in the future. So there's no end to the amount of information we want to be writing down and putting in our field books to help us. And those things are not just to help us figure out what we did during the day, but also to help us figure out things about the environment. We note things like what the rocks look like, and those things might tell us how the animal died and where it died and what kind of environment it died in. All of these things can help us recreate and help us with the science later on. So we observe, we take notes. We also include under the observation drawing maps. And that's another of the things that Jason Poole is really particularly good at. He's a paleo illustrator, paleo artist, and he would be out there all the time making maps of the bones inside the quarry. Everything to scale, everything to the north, and all of this stuff is really valuable information later on. We also took a lot of photographs. We took dozens of photographs of every single bone from every different angle. Again, everything you can imagine will help us. And on this stuff also helped us to plan. And planning is one thing we constantly did and do while we're in the field. We're constantly making plans so we can do everything that is safest for the people and the bones and most efficient. But we're constantly planning also because our plans are constantly getting thrown out of whack. Patagonia is famous for its wind and its crazy weather, and we certainly experienced that and sometimes got kicked out of the quarry by that crazy wind and weather. Sometimes you find bones in places you don't expect. Sometimes the bones are too moved in the way that we normally want to move them. So we are just constantly planning and changing our plans. Okay, so let's get back to the quarry. In these two pictures at the top, my friends are working on the tail section of this dinosaur. And so the next step is to start preparing for the jacket. In this step, we want to start trenching around the bones. We basically want to leave that bone where it is, dig a trench around it so it's now up on a pedestal. And the next thing we'll want to do before we start with the jacket is to put a protective layer on those bones. And in this case, a protective layer is just wet toilet paper, wet paper towels, aluminum foil, anything to keep the plaster of Paris from actually touching the surface of the bone. The next step is to actually start working on the jacket. Now, I often explain to people that a jacket is just like if you were to break your arm. Let's say you break your upper arm bone, which is your humerus. You would go to the doctor and he would put on that really hard white cast on there to protect it. That's almost exactly what we're doing, and even out of the same materials. I'm not sure that they use plaster of Paris for the cast anymore, but until recently it was just strips of material soaked in plaster of Paris that would harden and protect the bone and keep it from moving and anything from hitting it. That's exactly what we're doing with these jackets. We're just putting on a very hard protective layer to keep it from getting damaged. So our jackets are made of strips of burlap dipped in wet plaster of Paris. And then we soak those strips, and then we lay them down on the fossils very carefully, rather slowly, make sure that the bones are completely covered and have a nice thick shell around them. And then we just let it sit. That's the top jacket. We just let that top jacket sit and harden. And if it's a normal size jacket, a smaller jacket, it might be an hour or two. For some of our really huge jackets, it might be a couple of days. Regardless, we'll wait as long as we need to get it completely dry and really, really hard. So now we've got our top jacket on, and we have to start working on that pedestal again. And we want to start carving away at the bottom of that pedestal, so it really is more like a mushroom shape. And we want the bottom of it to be just narrow enough so it's almost ready to start breaking on its own. And at that point, we'll crack the bottom, and then very quickly and very carefully flip it over. And we do it quickly because we don't want the fossils to fall out of the jacket, or the rocks for that matter. But we do it carefully because they're very heavy. We don't want them rolling onto somebody. We don't want them rolling downhill. And we don't want to damage the bones inside. So in this case, we've had a very successful flip. And this is the step 2 where most paleontologists are the most nervous. You never know exactly how a flip is going to go. In this case, we have a very successful flip. Everything's still in place. We have a lot of excess rock there, so we'll start getting rid of that. Just leaving enough rock to protect the bone. And then we'll put the bottom jacket on. And this is how a normal jacket is made, a normal sized jacket. Right here, I have what we would consider a normal sized jacket, or on the smaller end of a normal sized jacket. This is a jacket we made this past summer in Wyoming. It's probably a fossil of an upper arm bone or humerus of a duck-billed dinosaur like Edmontosaurus. And this is a smaller version of a medium-sized jacket. If you can't tell, I'm really struggling right now because it's at least 35, 40, maybe 45 pounds. And that's just a smaller jacket. You can only imagine how big a truly huge jacket would be from our enormous dinosaur bones in Argentina. So to get those huge bones out, we have to modify the process a little bit, the process that I just described to you, because some of those bones are just too big, and they wouldn't flip properly, if at all. So we go back to our top jacket. It's dry. We're ready to start pedestaling. But instead of breaking it and flipping it now, we're actually going to dig tunnels in that pedestal. And that way we can start putting the bottom jacket on before it's actually flipped. And all of these strips of plaster and Paris of burlap through those tunnels will help keep all that rock together and all the fossils inside together. So we put most of the bottom jacket on, let it rest, sit, and harden up. And then we'll come back and start breaking the pedestal where it's still connected. And then we will very quickly and carefully flip it over again. And that's for the larger jackets that we can actually still move. We found while we were out there that a jacket the size of about a beach ball was the limit of anything we can move, because after that they just get too heavy. And the reason for that is you have to remember the bones are little more than rocks, and the rocks are encased in rock, and then we put a jacket on it, which is almost like another rock. So we have a rock within a rock within a rock. You can start to see how heavy these things really get very, very quickly. So in this case, we have another successful flip. We've got a really great jacket there on the upper left. There are only a few open parts of it where there was rock. And we have to now check those open spots for more bone. It can be hard to see, but in this picture, we have a big chunk of bone there and a big chunk of bone there. That tells us a couple of things. It's not a really big deal. We just have to be careful and really be aware of those things when we finish this jacket. But it also tells us that there's still bone left in the ground. And we have to be sure to get that and deal with that before we just move on to another bone somewhere else. So it's very simple. We just put on a few more strips of plaster of Paris and burlap to cover up those holes. And then for these nice big jackets, we wanted to be extra careful because we knew what kind of journey was in store for them. So we would cover up the entire thing with one more layer of nice wet plaster of Paris and just let it sit. Again, a lot of these things were enormous jackets, and we would have to let them sit for days. And then by now we're at the end of the expedition. We have to start getting some of these jackets out of the quarry. So as you can see there, those are the medium-sized jackets for us, which would be pretty big for most other expeditions. And these are about as big as we could move. And as you can see, it took every single one of us doing everything we could to move them at all. Sometimes we couldn't pick them up at all. We would just drag them as best as we could. But then there were other jackets which absolutely we knew from the beginning they were never going to move, not by us anyway. So we didn't even try to flip them. At that point, we brought in our friend Gerardo, who was a local rancher near Calafate, and he has a bulldozer. And a lot of people ask me at this point, well, if you have a bulldozer or a guy with a bulldozer, why didn't you just bring him in the first place to get rid of all that overburden? Well, the simple answer is that we just didn't have enough money. We had just enough money to send all of us down there for 2 months, to do the expedition, to survive, and bring this and get back. We only had just a little bit of money left over to bring Gerardo out there for just a couple of days to use his backhoe to pick up the biggest jackets, load them in his dump truck, and take them back to his property. The problem with that was that one of these jackets was so big that the bulldozer actually couldn't pick it up. We had spent weeks excavating, prepping, and then jacketing the entire hip section of this dinosaur. It is probably one of the largest jackets anyone's ever tried to make. And when he went to pick it up, instead of pulling it up like this, the bulldozer actually started tipping into the quarry. And it was a little scary at first, but once we realized what was happening and we made everything safe, we were pretty down for a day or two because we realized how much time and energy and materials had been spent trying to get that enormous jacket out of the ground. All we could do at that point was just cover it back up with dirt to protect it from the winter, come back the next year, break it up into a couple jackets, and then get it out that way. You never want to break bones up into multiple jackets if you don't have to, but there's just simply no way this was ever going to come out of the ground if we didn't do that. So here's an old paleontology joke. We're off. This is a big bucket of ribs, and there's Jason in the back of the dump truck with some of our larger jackets. Grand Gerardo would pick up our larger jackets, put them in his dump truck, and make trips back and forth from our quarry to his property to drop them off. And this is what his property looked like when we littered it with all of our bones. And this is actually a really remarkable picture and one of my favorites because it is very unusual to see that many jackets from any one quarry or any one skeleton. This is a really big deal, and it's also it represents an incredible amount of work. When we finally loaded up all these bones onto the shipping container, they told us it weighed about 16 tons. Now, one of the first questions I always get back when I get back from the field is, how was your vacation? And this is not a vacation. This is every day for 2 months from dawn till dusk, literally breaking rock, moving rock, and breaking our backs all day long on meager food rations for 2 months at a time, camping beside the river. It's physically demanding, but it's also mentally demanding. We miss a lot of things. We miss family. We miss nice soft beds. We miss food that isn't tuna fish for lunch every single day. But that's not to say that we don't love it. I, in particular, love every single second of this, and if I could go back out there right this second, I would. Now, a lot of people think, too, that most of the work is over. Well, much of the physical work is over. What's left is to load our bones all into the shipping containers, have someone else get that shipping container onto a ship, have the ship bring it up to Philadelphia, and at that point, we open up the container and bring all the fossils to labs just like this one. This is our brand new paleontology lab at the New Jersey State Museum, where we have volunteers just like these guys working on fossils, just like the ones from Argentina all the time. And it's a really great place. You can come by, you can talk to these guys about what they're doing, ask them what they're working on and where it came from. It's a really great place. And this is where actually the science starts to go. You know, when you're out in the field, your job is to get those bones out of the ground as quickly and as carefully as possible. It's not until you bring it back to the lab and start cleaning them up and really start studying the bones, looking at every single surface of every single bone and their shapes and their colors and their size. And that's when you start to learn something about this animal and how it lived. So this is where the science really begins. And this is not the fun part, but it's another fun part and just a different kind of work. Now, this is usually where my talk had to end because since we found this thing, it has been a big secret. We haven't been really allowed to talk about it. We haven't been able to say its name in public until about 6 weeks ago when we finally announced this dinosaur to the world. And if you haven't heard by now, this dinosaur is named Dreadnoughtus schrani. And this is one of, if not the largest animals ever known to walk the earth. Its name Dreadnoughtus actually means fears nothing. And we named it after the first group of true battleships that came about 110 years ago that were called dreadnoughts. And they were so big and had so much armor that they were basically completely impervious to anything else out there at the time. And that's why we gave this dinosaur its name. It was so big that once it reached even medium size and certainly adulthood, it was so big that it had no predators and really didn't have to worry about anything. Now, there are a lot of really awesome things about this dinosaur, not just its size. but the fact that it is so complete. Whenever a paleontology expeditions go out and find a skeleton, if we find 25% of a skeleton, that's a big success, and it's pretty unusual. In this case, we have 80% of the skeleton. The only large chunk of the skeleton we're missing is most of the neck and much of the head. But what's really cool, one of the cool things about this dinosaur is that we actually have part of the head. We have one tooth, and we have a very small section of the jaw. And this is really unusual because with these dinosaurs, all of the sauropods, out of all the sauropod skeletons we know of and we only have maybe a dozen, 2 dozen skulls. For whatever reason, the skulls of these animals, when these guys died, the heads just popped off and floated away in the rivers. We just don't have many skulls. So the fact that we have even 2 little bits of the skull is a really big deal. It's also, of course, really cool because it is so enormous. This bone that I'm sitting beside is certainly not one of the biggest bones in the skeleton. That's just one of the lower arm bones, like the shin or your radius or ulna. The femur is actually taller than I am and bigger around than I am. This was truly an enormous dinosaur, and we can calculate its weight to be about 65,000 pounds. That's the equivalent of, 65 tons. That's the equivalent of about 12 male or bull African elephants all crammed into one body. And we came up with this really nice graphic here to show roughly how big it was. It was almost as long as a Boeing 737, certainly taller than one of those planes, and it was truly, truly a giant. If you had been anywhere near it while it was walking, you literally would have felt the ground shake around you. So this is a really special dinosaur in a lot of different ways. And at that point, I really appreciate you guys joining us, and we'd be happy to take any questions that you have. I believe you'll just have to type them into Hangouts. Sure. Okay.
So just for the folks out there, just to let you know, I'm just going to go in this shot. Just to let you know, if you wanted to add your comments or questions, you can just select between on the upper right-hand side. You can select the Q&A and go ahead and type in your questions, and we'll moderate as we go. We'll read your questions out loud. And also, if you are on the YouTube channel, you can always comment, and we can monitor those as well. Now, we know that there's a slight delay, so we're just going to give it some time to populate.
And while we're giving you guys some time, I want to mention, too, that we do lead expeditions out to Montana and Wyoming every summer. Just about anybody is welcome to go. We take teachers, we take students for college credit, we take older retired folks who are just interested. We had high school age kids last summer. It's a really fantastic trip, and it's an amazing opportunity, and we take just about anybody, and I invite anybody to come along with us. Okay. All right, someone asked, when did I decide to become a paleontologist? In the last show, I was just telling kids, or basically answering the same question, and I have always wanted to be a paleontologist, and I think if you ask almost any paleontologist living today, they would tell you the same thing, that we are doing exactly what we always dreamed and wanted to do. So in that way, I consider myself to be really lucky. There were other things I wanted to do when I was a kid. I wanted to be an astronomer. I wanted to be an oceanographer. But paleontology was always the strongest. And when I was younger, my father took my brothers and I out on fossil hunting trips, and I've just always been hooked on it. Sure. I know that kids often ask about what kinds of dinosaurs we find in Montana and Wyoming. We are searching in rocks that are right at the end of the Cretaceous period, so right before the dinosaurs went extinct. So a lot of the common ones, Triceratops, Tyrannosaurus rex. This past summer, we found a really great Tyrannosaurus rex skeleton and skeletons of at least 2 other dinosaurs. We weren't able to excavate any of them because we didn't have the proper permits yet, but we will this summer. So this summer's dig that I was just mentioning is going to be a lot of fun and a really big deal. We did get to excavate a good chunk of a skeleton of a Pachycephalosaurus, which if you don't remember your dinosaurs, the Pachycephalosaurs were the ones that stood on 2 feet, and had the really thick domed skulls that they would probably use to kind of ram into each other. Okay, we have one more. How far is it to Argentina? Well, I guess it depends on where you're going in Argentina. Where we go is about 6,000 miles to Buenos Aires, but it's another at least 1,000 miles down to El Calafate. So we're actually closer to Antarctica down there than we are to Buenos Aires. So it's a long ways. A lot of people often ask too, do we get to keep the bones when we go out to Montana and Wyoming? It depends on where we are. If we are on private land where we've been given permission to do so, yes, we can keep the fossils. If we are on public land, like Bureau of Land Management land, which is where we are most of the time, they actually have very strict rules about what you can and cannot keep. If it's a plant or an invertebrate fossil, yes, you can keep them. If they are vertebrate fossils, you absolutely cannot keep them, and you can even get thrown in jail for doing so. Even the fossils that we collect for the museum, those fossils go inside of our museum, but we actually hold them and they remain property of the federal government. So there are very strict rules about doing that. The next question is, what is the best part of being a paleontologist? There are a lot of fantastic things about being a paleontologist. I would say maybe one of the best easily is that I get to travel a lot. And that was one of the things that first drew me to paleontology, is that I knew I would get to travel a lot. You get to travel to a lot of the most remote, natural, and pristine places left on the planet, which I absolutely love. But I get to go all over the place. I'm going to Germany in a few weeks. I was in London back in June. I was in China a few years ago. And I just love to travel, and especially to see all these natural places left on the planet. So that's it. So, okay, someone else asked, where is the dinosaur now? From Oliver Street School in Newark. That's a great question. Right now, the dinosaur bones are being packed up because they have to go back to Argentina. Argentina is like most countries in that they consider all their fossils to be national treasures. So one of the parts of the agreement that allowed us to go dig it up was that after 3 to 5 years of studying it, we had to send it back to Argentina. And we are perfectly happy to do that because they're right. It is their national treasure. One of the great things we can do today, though, with technology, which didn't even exist a few years ago, is that as we were studying it, we were scanning all of the bones with a 3D laser scanner and putting all of that data into a computer. So nowadays, all we have to do is feed that data into a 3D printer, have it print out more dinosaur bones, and at that point, someday we can actually print all the bones and put it back together and have it on display. Right now, it's not on display anywhere, but one day it'll probably be at the Academy of Natural Sciences in Philly or at Drexel. Okay. All right. Another question is, how many dinosaurs have I discovered? I have not yet discovered any new dinosaurs, unless you consider this Argentina one. But I have found pieces of dinosaurs, hundreds and hundreds of really good pieces. A lot of people ask me, like, how many dinosaur bones have I found? If you consider all the little fragments I find on the ground, thousands and thousands and thousands. Because again, there are places where you can go and you literally can't step without stepping on bones. They're just littering the ground. So I haven't yet discovered any new species, but one day I will, and I already have some names picked out. But if you're just asking about bones, lots and lots and lots of them. And if you were to go out in Montana and Wyoming with us, I'd have you finding bones like that. Okay, someone else asked, how would an average student get involved in paleontology? That's a great question. Most paleontologists now go to college studying either geology or biology, and most of them now are biology. But that's okay, because that just means we need more geological paleontologists like myself. But it's not restricted to those. All you really have to do is go to school and study science and do that for a really long time. You pretty much have to get a PhD to be a paleontologist. You just have to love science, and you have to love nature, and you have to love studying. Because even when you get your PhD, you still need to be learning things every single day for the rest of your life. So I'd say the first thing you have to have is a real love for science and learning. Okay. Another question is, what kinds of dinosaurs are in New Jersey? That's a fantastic question. A lot of people don't realize this, but New Jersey is a fantastic place for paleontology, and it was actually southern New Jersey and Philadelphia are the birthplaces of paleontology in the New World. And that's because 100, 150 years ago, all of the world's best and biggest paleontologists were working and or living in that region. So all the first fossils found in the New World were basically found in that area. The world's first nearly complete dinosaur skeleton is a dinosaur called Hadrosaurus folkii, and it was found in Haddonfield, a little town in Monmouth County, New Jersey. The world's second nearly complete dinosaur skeleton was also found in New Jersey, roughly the same area. It's a dinosaur called Dreadnoughtus, which a lot of people don't know about, but it's actually just kind of a smaller version of a T-Rex, and that lived at the same time as the Hadrosaurs. So New Jersey is a fantastic place for dinosaurs. Okay, someone else from Oliver Street asked, typically how many bones can be found in a dinosaur? Oh, that's a great question too. It kind of depends on the dinosaur, but most dinosaurs had basically the same number of bones. Oh, and if I remember right, I'm gonna take a guess, and it's somewhere between like 120 and 160 bones. I honestly don't remember exactly, but it's a lot. Okay.
We have two questions. One is what you set up. The second one is, are you going to assemble the full skeleton?
Okay. We have a couple of questions. One of them is, will the Dreadnoughtus be reassembled and displayed? Hopefully no one will ever try to reassemble the actual bones because they're just too big and too heavy and probably would collapse and be destroyed. Eventually someone will definitely print out those bones in 3 dimensions and put that on display. And it would probably be at the Academy or at Drexel University. But right now there are no firm plans to do it right away. They're still actually studying this dinosaur. We published this about 6 weeks ago, but we're going to be studying this dinosaur for years, so that's keeping us busy. And you'll have to remind me about the other question. What is the coolest dinosaur I ever dug up? I really have problems with those favorite questions. This was certainly one of, if not the coolest dinosaurs, and not just because it's so big and because it was so new, but because of the entire experience. Working so hard to get this dinosaur out of the ground, going to such a beautiful and remote spot. But I feel like every dinosaur that we dig up is really cool. Like I said, we excavated that Pachycephalosaurus this past summer. That was really cool because I've never dug up one of those, and even though they're a popular dinosaur, we don't have very many of their skeletons at all. So anytime we find any parts of that species, it's a big deal. Before I got into dinosaurs and when I was still in school, I used to live in Alabama, and there aren't many dinosaurs in Alabama, but there are a lot of rocks that have a lot of things that lived in the ocean at the time. And there's some normal things like turtles and fish and crocodiles, but there were also really cool things living at the same time as dinosaurs like mosasaurs, which are just giant swimming Komodo dragons that were just as big and probably just as mean as the dinosaurs. And so I had a lot of fun excavating those. I dug up a baby mosasaur once that was only about 6 feet long, but perfectly articulated. It was a gorgeous specimen. So every species, every specimen is a little bit different and almost equally cool. They're just different, no better or no worse. Another question is, do dinosaurs have blood? Well, they don't anymore because they're not living, but yes, they did have blood, and they had a lot of blood. In fact, that's one of the things we've tried to figure out is how can a dinosaur as big as Dreadnoughtus have a heart strong enough to pump that blood all the way to the end of the tail or the neck to get to its head and pump it back. That's one of the things we've been really trying to figure out. Another question is, which dinosaur species would you be most afraid to meet? There are plenty of those. The new Spinosaurus that just came out, that would be pretty scary. T-Rex, there's no escaping a T-Rex. But there are a lot of ones that I would hate to meet in a dark alley. Even like Velociraptor. Everyone thinks Velociraptor was this really big, scary dinosaur because that's how they saw it in Jurassic Park. A real Velociraptor is only about the size of a large turkey. So just picture a large angry turkey with a long tail and big teeth. And if those guys actually hunted in packs like we think they may have and like wolves do, it wouldn't matter that it was only the size of a turkey. They still would have taken me down and ripped me apart in seconds. So there were plenty of dinosaurs to be scared of back then. And the only reason we're here today is because that meteorite came and wiped out the dinosaurs. Another question is, did I ever find a dinosaur egg? I have yet to find a whole egg, but I have found tiny little fragments of dinosaur eggs. And those are some of my favorite finds ever, just because they're so rare and they're so cool. And those pieces I have found in Montana and Wyoming in our field areas. And the first dinosaur eggs ever found outside of China were found just outside of our field area. So one of these days, we're going to find whole eggs. And if we're really lucky, we'll even find whole nests. But at this point, just a few tiny little fragments. But that's pretty good, too. Next question is, what is the smallest dinosaur I have ever found out in the field? I haven't found many small dinosaurs. Most paleontologists will tell you that technically speaking, dinosaurs are not extinct, that birds are dinosaurs. And we have found bird bones, so you could consider that to be the smallest dinosaurs I've ever found. Other than that, if you're talking about traditional dinosaurs, that Pachycephalosaur might be the smallest thing I've ever found, and those are still pretty big, at least a good bit taller than I am and bigger around than I am. A lot of people wonder about the small dinosaurs, why there weren't very many. There were probably lots and lots of small dinosaurs back then, just like there are lots of small animals today. The problem is it's a lot easier to find big bones than it is small ones, and small ones usually are more fragile. So that's why we think we just don't find many small dinosaurs. We're finding them more and more, though. Another question is, how would I know if the bone I found was a dinosaur bone? That's a really good question. And it depends on a lot of things. If you find one in your backyard, find a bone in your backyard, and you live in North Jersey, you can bet it's probably not a dinosaur bone because they just don't have the right types of rocks up there. So again, it goes back to being in the right place, making sure that you're in a place where dinosaur bones could be. After that, though, it can be kind of tricky. We find bones in Montana and Wyoming all the time that we can tell it's a piece of bone, but we don't know if it's dinosaur or if it's crocodile or turtle or anything else. You have to look at different surfaces. You have to consider things like size. If I find a bone this big in Montana, where we are, it's a pretty safe bet that it's too big for any of the crocodiles that lived there, so we could say it's dinosaur. Sometimes you'll find bones that have a certain very specific texture on them, and that's a turtle bone. It just all depends on what you've learned. To be a paleontologist, you have to be really good at anatomy and study it and study bones, or osteology. So it's just a matter of experience and being able to recognize certain features that you see in bones to help you figure out if they're dinosaur or not. But again, when you do that out in the field, it's more of a game than anything else, trying to figure out what it is. It's not till you bring it back in the lab that you really are concerned about what type of bone it is. Oh, that's a good question. Someone asked, did any dinosaurs hibernate? We don't know for sure, but we think that some of them probably must have, because we have found dinosaurs on every single continent, even Antarctica and northern Alaska. And those places, even though the continents have moved since then, especially Antarctica, has basically always been near the South Pole. So even though it was much warmer then, it still got dark for several months out of the year. And dinosaurs were reptiles, meaning they're cold-blooded, which means they have to get a lot of their energy from the sun. So if there is no sun, we think that they must have had to hibernate, at least those near the poles. Here's a good question. Where am I traveling to next? Well, in a few weeks, I'm going to the big international meeting of paleontologists that will be in Berlin, Germany, which I know is not exactly what you're asking me about and is not as exciting. The next field expeditions I'm going on, at least as far as I know, are back to Montana and Wyoming. We go there every summer for about a month. But you never know. I have lots of friends that go to all kinds of places, and they know I love field work, and they almost always need extra help. So I tell them anytime they need help, call me, and I'll get to wherever you are as quickly as possible. I love the traveling, and I'll take any opportunity I can to go just about anywhere. Okay, we can take a few more questions if anybody has any. There's one. How do we know the colors of dinosaurs? That's a great question. And the answer I would have told you 10 years ago was we absolutely don't know what the colors were. All we can do is make educated guesses. If you go out in nature today, I mean, any dinosaur technically could have been flashing neon pink and green because there's no way to prove otherwise. But it's really unlikely because if you go out into nature today, you're not going to find any animals that are flashing neon pink and green. You're going to find the vast majority of animals have some kind of colors or patterns that are used to give it camouflage, either to hide from predators or to be able to sneak up on animals to eat them. So it's a really safe assumption to assume that dinosaurs had similar colors and similar patterns. What's really amazing though, and this is brand new in paleontology, just in the last 5 or 10 years, we have started to use all this amazing technology to figure out things that we never thought would ever be possible in paleontology. And a friend of mine in the United Kingdom actually uses incredibly bright X-rays and other really high, amazing technology to blast fossils with these X-rays and start to figure out pigment patterns. This is not necessarily colors, but we can start to figure out the patterns of colors that are still left inside the rock. So again, we're not figuring out colors yet, but figuring out the pigments is the first step to figuring out. Brand new in paleontology. All right, another question was, I think I saw, why did Stegosaurus have spikes on its back? That's a great question. If you remember Stegosaurus, that was one of the four-legged ones and had a line of spikes along its back, and then I think the jury is still out on those. I don't really study stegosaurs, but I think the jury is still out. People used to think that they were used for defense, but if you look at how they're built and how they're structured, they really weren't very good for defending themselves. So the next best guess is maybe they used them for some kind of thermoregulation, basically giving off excess heat or absorbing heat from the sun in the morning. It's also a safe assumption to say that they were probably used for display, so for attracting girlfriends and boyfriends, or to tell other members of its own species who it is, like what individual it is. There are always multiple answers to these questions. Display is always a safe one, and after that it's probably thermoregulation, but we're just not sure. The next question is, how were there so many enormous dinosaurs, but today's animals don't get to be that large? That's a great question. We're not exactly sure why that is today either, but one idea we have is that everyone knows it was much, much warmer back when dinosaurs were alive, and part of the reason for that is that there were a lot more greenhouse gases in the atmosphere. There was a lot more carbon dioxide in the atmosphere. So if it's warmer and there's more carbon dioxide, you can grow a lot more plants, even a lot more plants within one small area. If there are more plants, that means there's more food for the plant eaters without having to use a lot more energy to get it. So if you have a lot more food available to you, it lets you grow evolutionarily to have much bigger body size. It's not a 100% satisfying answer, but that's probably the best guess that we have right now. Okay, then the next question is, could dinosaurs live today? Well, again, technically dinosaurs are living today because birds are dinosaurs. But if you mean like the traditional reptiles, I don't see any reason why they couldn't live in certain parts of the planet. They are not living today. That is not at all what I'm saying. But if we were able to bring them back and put them on an island in the middle of the ocean, I suppose it is theoretically possible that they could survive, but I think we've seen how that works out, so we probably shouldn't try that. Maybe one more question? See if we have any more questions. I think that's it. All right, thank you guys so much again for joining us. Feel free to come by the museum to check out our lab. Feel free to contact me if you're interested in going on that dig. And thank you again, and have a great day.